very shiny, and then as you scan it, so we get all these nasty reflections. It's very difficult to deal with. So we had to solve those problems before. One day Steve contacted me, asked if we could actually do a scanning of the metal structure, because I think they had tried before. And then, well, we just had to come up with scanning 200 objects on Museum Sheffield. That's okay, that's fine. We just went in the same way. So we went on a roll, so right, just give me the... So in the end, we scanned it twice, just to be sure, the statuette, the man of steel. Well, the scanning itself, it took about 1.5 to 2 hours at the most. But then, because you have an object, you put an object on a table, so you scan one side, you turn, scan another side, and then you end up with several surfaces in 3D, and you need to register them to put them in exactly correct position. And that work, it takes ages, and it took, ideally in 1 or 2 days you do, but we wanted to do a good job, and then because in the end, when you have too many surfaces, the errors, it's very difficult to join them up exactly. So you need to zoom in and then delete some vertices in 3D that are not right. So in the end, we had to stop at some point. For instance, let's see if I can show you, zoom in. For instance, here you can see there are some data here. There is some data points that could be pushed a bit to the side, but okay, when you zoom at this level, you wouldn't. So of course you can actually, when you have this, you can show all the here we got 1 million data points on this structure. You can see the data points in there, so we can show only the vertices or the connected, and then we can hide it, because here you show the vertices that are on this plane, you can see, but show the back as well. So you could actually hide the back one, so then you can only see the myself and my research assistant Marisa Corman. So we both of us, we did the whole Museum Sheffield, and we did that. So it needs to be 2 people to do, because he needs to handle the scanner and the computer and press the buttons at the right moment. So in the past 5-6 years, we developed our own scanners. So we started developing with laser scanner, a single stripe, and then we went to visible white light, multiple stripe scanner. So we have several patents on the scanning and the scanning techniques, 4 patents, and we license the techniques to company in Europe, in Germany. So there's a company, they have a 3D scanner for face recognition entirely based on our technology. So we licensed the whole code and the technology to them. And last year we licensed to this other company in California. So they are trying to exploit our technology in different markets. So when we first funded for that GISC project in Museum Sheffield, we had different techniques we could apply, either laser light or single or multiple stripes. In the end, a single laser light was the technique that worked best. We tried several. We tried infrared. We tried all the things that we tried over the year, to see which one worked best in metals. So the conclusion is single line, laser light, that's the best, because you can control say, if you project a light on a flat object, it reflects straight in lots of noise. But if you project an angle, the noise goes off, and then it's not that you don't get noise, you still get, but the amount of noise is massively reduced. Before license to this company in Germany, we tried our technology at Heathrow Airport for security, and that scenario was we just tried on Terminal 1. That was a try, because they tried fingerprint, iris, and 2D and 3D face recognition. So we were in a 3D face recognition. So the idea is you go to check-in. At the moment check-in, you get a barcode, and there you have your faces 3D scanned. When you passport control, and then another 3D shot is taken, and then check in 3D if you are here. You need to scan a person, verify in 14 seconds, and then they're reduced to 10. But anyway, we can do in 1 or 2 seconds, so we're always alright. When the official look at the passport, the image, and then looks at you, saying, is that same person? It's a very difficult, you need to be really trained to that, because, especially people from different ethnic groups, and it becomes difficult. You are very good at recognize maybe people from your own group, but from different groups it becomes difficult. And then, so that is, what techniques could you develop to improve this, to train the person to say, yes, that's the guy on the picture. It's very difficult. The iris, because it's very difficult to, you need to put your face on, and they say, yeah, iris is 100% accurate, but there are 4% of the case you cannot get an image for one reason or another, So, okay, if you discount the 4%, then it's 100%, but what about the 4% you cannot enroll for some reason, because they have a, What happened next is this company in Germany, they are working in security, are developing this 3D scanning for security, and then so they have a 2D face recognition and a 3D face recognition. When they start with 3D scanning, people ask this question, what is it good for? And I say, right, what's it good for? That's what the car industry, all the industry users say, right, you have a product here, but you don't have the drawings any longer. You don't have a 3D model on your computer. So you can just scan, and then you produce new CAD drawings, and then you can modify the design and go that way. But now I think the manufacturing went the other way. Now everything is done as a CAD model first, and then you only do the scanning on object when you don't have a real CAD model. Well, some objects are very complex, it's very difficult to draw, and then it will be easy just to scan. It's very, so if especially it involves some artistic design, there's no real function, but it's nice looking. It's part of its functions, looking good.